Alright, let's look at part 5. We're going to derive the lever rule, and we're going to use it to explain the ratio of vapor to liquid fraction change in a closed system as the temperature is fixed and the pressure is increased, and as that transitions from all vapor to all liquid. So let's look at that. So we have pressure versus mole fraction of the most volatile compound graph. On the top we have liquid, at the bottom vapor, and then we have our equilibrium curves of the dew point and the bubble point. Say we are right smack dab at 50% concentration, and we are at about half pressure, so we're right here in the middle. To the left, to the right rather, lies our vapor dew point equilibrium line, and to the left lies our bubble. Oh, that's bad. Hold on. Bubble point is on the left. Bubble point's on the right. Dew point's on the right. Left. Left. Right. Okay. Anyway, so this is your x1. This is your y1. And then this, of course, is your z1. So what we are looking at right now, the lever rule, is the differences. Well, that was bad. And these. So this is going to be your y1 minus z1, and your z1 minus x1. The relationships between those two are your lever rule. We can derive that. So we know that we know that the flow is equal to L plus V, Jesus, or the liquid and the vapor portions. We know that that can be written like this. The flow component times the mole ratio of the flow is equal to the mole ratio of the liquid plus the mole ratio of the gas, of the vapor. You can then rewrite that as this. You can expand it. Can isolate. Then we can get L and V on the one side. And there is the derived lever rule. So, as you can see, these two portions of the lever rule correspond directly with the differences in the vapor and liquid portions of our system. And as you can see, as the vapor is increased, we go from having all vapor, a split between the two that eventually starts with very little liquid to increasing liquid at the top. So when we hit the dew point, we just start making liquid, right? Yes. And it slowly increases until we get up here, and the vapor portion slowly decreases as we go up. until we have no more vapor left. And when that happens, this ratio gets smaller and smaller on this side and larger on this side. Again, this cannot be more than 1, but as the pressure is increased, it becomes all liquid at the top, which means that this side of the expression is just going to 1. And that is the lever rule. Thank you. Carlos, I just want to say thank you for a great year. I look forward to having you in Transport 1 in the fall. I really appreciate your teaching style. I feel like I actually learned a lot of things pertaining to chemical engineering as a profession and as a major, and I feel like I would not have learned those things if I didn't have to spend all this time and effort looking at the YouTube videos and making these YouTube videos. So I really appreciate everything you do for us, and I hope you have a great summer.